Good morning, children. Sairam. Children, in the previous presentation, we have already completed the transition elements. We have started the transition elements and their properties like alloy formation, colored compounds, interstitial compounds, catalytic behavior. We have already discussed, and I have told you that the two compounds that are potassium permanganate and potassium dichromate have been removed from the syllabus. We don't have to study the preparation properties and uses. Now next I'm starting with the inner transition elements. They're called the F block elements. Now inner transition elements are those elements which are kept separately outside the periodic table, but if you see to the atomic number of the inner transition element, then the first one is cerium, atomic number 58, which actually should come after lengthenium. Lengthenium is having atomic number 57, after which is cerium, and then prodymium, neodymium, and so on. Now the last element in these elements, the inner transition elements, they are further divided into the two groups. The first 14 elements which follow lengthenium are called the lengthenoids, and the next 14 elements which follow actinium are called the actinoids. Now you all can see that the lengthenoids, the last lengthenoid is having atomic number 71 and is lutetium, and 72 is hafnium, which is kept in the D block of the periodic table. Now actually why these elements from cerium to lutetium and thorium to lawrencium are kept separately outside the periodic table? It is because these elements, though their series of atomic number are after the D block elements, but in these elements the last electron enters the f orbital. They should come inside the D block but are kept separately and are called the inner transition elements. Now children, there are two series, as I have told you, the lengthenoids and the actinoids. Only three things we have to study in this lengthenoid and actinoid. If you see the PDF for the syllabus, only three things we have to study. I'll tell you. Just a minute, children. Yes. Now see, in the syllabus for D and F block elements, we have to study the electronic configuration, the oxidation state, and the lengthenoid contraction and its consequences. The actinoids we don't have to study. We have to study only the electronic configuration, the oxidation state, and lengthenoid contraction and its consequences. So I'm starting with the lengthenoids. What are lengthenoids? The lengthenoids are the 14 elements following lengthenium, and lengthenium closely resembles all the lengthenoids, so the 14th elements are called the lengthenoids. What are lengthenoids? If somebody asks, you'll say lengthenoids are the 14 elements which come after lengthenium but are kept separately outside the periodic table because the last electron enters the f orbital. Now if we see the electronic configuration of lengthenoids, the first lengthenoid is lengthenium. The configuration, lengthenium is closely resembling the lengthenoid, so it is included in lengthenoid. It has the configuration 5d1 6s2. 2. Now cerium is the first one. The configuration is 4f1, 5d1, 6s2. Now the configuration for the ions also is given. You all can see. Children, these electronic configurations you have to remember little bit. The second one is Parasodimium. The configuration is 4f3, 6s2. Neodymium, the configuration is 4f4, 6s2. Promethium is 4f3, 6s, 4f5, 6s2. Now samarium 4s6, 4f6, 6s2. Europium 4f7, 6s2. Then you all can see the configurations for gadolinium. The configuration is 4f7, 5d1, 6s2. This is the exceptional configuration. Why it is so? Because in order to have 4f7, that is the half filled configuration, the next electron instead of going to the 4f orbital resides in the 5d orbital. After 4f7 is just 4f9 for the next element. So this is all about the electronic configuration. Now coming to the oxidation state. In lengthenoids, +2 and +3 compounds are common. Mostly they show either +2 oxidation state or +3 oxidation state. However, occasionally +2 and +4 ions in solution or in solid compounds are also obtained. It is due to the extra stability of half filled, fully filled and empty F subshell. Now what is lengthenoid contraction? The important topic is lengthenoid contraction only. Now children, if we see to the graph of the atomic number and the ionic radii, you all can see that the ionic radii continuously decreases with the increase in atomic number. This decrease, the overall decrease in the atomic and ionic radii from lengthenium to lutetium is the unique feature in the chemistry of lengthenoid and is called the lengthenoid contraction. Now, many a times in the board exam the question comes, what is lengthenoid contraction? You'll say it is the overall decrease in the atomic and ionic radii from lengthenium to lutetium. Now, what is the reason for the lengthenoid contraction? The reason for the lengthenoid contraction is the imperfect shielding effect of one electron by another in the same subshell. So, what is the reason for lengthenoid contraction? It is the imperfect shielding effect of one electron by another in the same subshell. Now, consequences of lengthenoid contraction. The important part, the radii of the members of the third transition series are very similar to the corresponding members of the second transition series. That means the atomic radii of these elements is very similar to these elements, but as per we know, the size of atom should increase down the group. That means the zirconium and hafnium should be smaller, hafnium should be bigger, but actually zirconium have and hafnium have almost similar size. This is one of the consequences of lengthenoid contraction. It is because lutetium, the size from here to here is decreasing according to the lengthenoid contraction because of the imperfect shielding effect. Now similarly, hafnium size is also not very big. It is also decreasing, due to which zirconium and hafnium is almost similar. Similarly, these elements, all these elements have sizes almost similar to this element. So it Because of this, identical radii, they occur together in nature and are very much difficulties faced in their separation. This is the consequence of lengthenoid contraction. So again, what is lengthenoid contraction? Lengthenoid contraction is the regular decrease in size of elements from lengthenium to lutetium. Now, what is the reason behind lengthenoid contraction? It is the imperfect shielding effect of one electron by another in the same subshell. Consequence of lengthenoid contraction, the size of the third transition elements series of elements is very similar to the corresponding members of the second series. One more consequence you can say, very much difficulty is faced in the separation of zirconium and hafnium. So this was the last topic of the chapter and the chapter is complete. We can discuss some of the questions. Only few questions we are discussing. Rest you have to solve yourself in your fair notebook. You can download the PDF for NCERT solution and write down all the answers in your fair notebook. But kindly solve only those questions which are related to those topics which are still there in syllabus. Now, first question is, on what ground you can say that scandium is a transition element but zinc is not? Now, what are transition element? As I have told you, transition elements are those which has incompletely filled d orbital in their ground state or in their most stable oxidation state. But if we see to the electronic configuration of scandium. Scandium, the configuration in ground state is 3d1, that is incompletely filled d orbital. For zinc, if we see, it is 3d10, the d orbital is completely filled. And if we see to the most stable oxidation state of zinc, it is Zn 2 positive. In 2 positive also, the 2 electrons which are present in the 4s subshell are ionized and the d orbital configuration remains 3d10 only. So, scandium does not have incompletely filled d orbital neither in the ground state nor in the most stable oxidation state, so is not regarded as the transition elements. Another question is, silver atom have completely filled d orbital in ground state, still we call it transition element. Why? Because for silver in ground state the configuration is 3d10, but if we see Ag2 positive, in that the configuration is 4d9, that means have incompletely filled d orbital. Next question is, why do transition elements exhibit higher enthalpies of atomization? That means when two atoms of transition elements are combined together, we need a lot of energy to separate them. Why? It is because of large number of unpaired electrons in their atoms and they have strong intermolecular interaction, so we need to apply more energy for atomization. Next is, name the transition element which do not exhibit variable oxidation state. Children, when we were discussing the chapter, I have told you that in transition elements, scandium shows only +3 oxidation state, zinc also shows +2 oxidation state, but zinc is not a transition element, only scandium is the transition element. Zinc is a d block element but not a transition element. So the element which show the transition element which cannot show variable oxidation state is scandium. Next is, calculate the magnetic moment of the divalent ion in aqueous solution if its atomic number is 25. Atomic number is 25 and is divalent. That means configuration is 3d5 4s2. Now d5 4s has 2 electron, but as it is divalent, that means it has given 2 electrons, so the configuration is 3d5. Number of unpaired electrons are 5. Now with atomic number 5, the divalent ion in aqueous solution will have d5 configuration, so we'll have 5 unpaired electrons, and we can calculate the magnetic moment mu is equals to n plus 2. N is 5. 5 plus 2 becomes equals to 5.92 Bohr magneton. So this is the calculation of your magnetic moment. So children, kindly do practice such questions, all such questions, and write down the answers in the NCERT exercise in your fair notebook. Download the PDF and write down the answer. If any question you're not able to understand anything, do ask me in the live class. Thank you children. Sairam.